Hi guys, in this video we'll begin our look at elimination reactions. This cover page of the handout shows a synthesis of the drug Tamiflu, which is used to treat influenza. It's a multi-step synthesis, but in one of the reactions going from 63 to 64, we see an example of an elimination reaction. This is an iodine here, and this is our leaving group. And in this reaction, the iodine is not substituted, it's not replaced, but it is eliminated, it's removed. But along with the iodine, there's also a hydrogen removed. It's an example of a beta elimination. The beta refers to the hydrogen that's removed, the leaving group being on the alpha carbon. This is an example of an E2 elimination. We'll see with elimination reactions we have both E1 and E2 with similarities to the SN1 and SN2 reactions. Again, both substitution and elimination both occur with substrates that contain leaving groups. And the leaving group information that we talked about in the substitution handout applies to the elimination reactions as well. Now there's a couple of different reactions on this synthesis of Tamiflu of interest. The first one's actually a Diels-Alder reaction, 4 plus 2. It's actually an antioselective because a chiral catalyst is included. We've not talked about that, but they just get one enantiomer in a greater than 97% enantiomeric excess. Here we see a radical bromination. We'll talk about that reaction near the end of the course. There's another elimination down here and going from 69 to Tamiflu, compound 1. That's an E1 elimination. It's a little more involved. Once we go through a little bit, you can look back and see if you can understand this E1 elimination, where the leaving group here is actually the Bach group. A little more complex, just a touch. Not a traditional leaving group. It's actually an oxygen leaving group that's leaving. And how do you make oxygen a better leaving group? Protonate it with strong acid. That's why the phosphoric acid in this case is used. There are, of course, more details there to understand. Okay. Beta elimination at a tetrahedral carbon. General line reaction. Again, a substrate, tetrahedral carbon with a leaving group, denoted X here. Now, this intro is very similar to my intro for the substitution reactions. If you remember, we started with a general line reaction. We then gave a more specific line reaction, and then we showed two different mechanisms. I will show them both, then we'll discuss which one is correct for the example reaction given. Okay. So in an elimination reaction, the leaving group is removed along with a hydrogen. And we ultimately put in a double bond. Okay? We typically are going to make alkenes. More broadly, a pi bond, but most commonly it will be a carbon-carbon pi bond and thus an alkene. Now we're going to employ a base. And the base actually takes that H And the H again is not on the first carbon, which can be called the alpha carbon. It's on the next carbon, which is called the beta carbon. And again, beta elimination, that refers to the hydrogen that's being taken. And then the leaving group leaves as well. The base takes the H. The leaving group is going to leave and take on an extra lone pair and often become minus, but not always. And we put in a double bond. When the leaving group is halogen, this mechanism is also called a dehydrohalogenation. We are removing a hydrogen and a halogen. Again, when the leaving group is halogen. Okay, broadly speaking up here, a precise example, if we take this alkyl bromide, react it with T-butyl oxide or tert butoxide. We can do a beta elimination to get this alkene. The leaving group leaves, becomes Br minus, and the base is taken an H. Now, let's make sure we understand how this pi bond came about. All right, there's two H's here. Well, there's only one here now. And so you see we have removed both the H and the bromine, and instead of this carbon bonded to something else, it's double bonded to this carbon, and instead of this carbon bonded to something else, it's double bonded back. Okay? It's an elimination reaction. It's actually the exact opposite of, okay? You can say we're removing HBr. Now, we don't actually form HBr. This is just a general assessment of what's being removed, an H and a Br. If we add HBr back, that would be an addition reaction. And that was our main reaction during test 2, addition of HBr to an alkene. The only problem is if we added HBr to this alkene, we wouldn't get that product. So that actually is a little bit not exactly correct. We would actually get the bromine here, right? So in this case, it wouldn't give that exactly back. But you see that these are isomers. We can add HBr to this and get back an alkyl halide. Or we can start with an alkyl halide and remove HBr to make an alkene. And that's the way we're going when we eliminate. Again, we don't actually create HBr. We're going to create Br minus. And in this case, we'll create this alcohol because the base took the H. Okay, let's look at a mechanism for this. Get into more details of what's going on. All right, first I'm going to show an E1. If we think about it, what can we do? The leaving group has obviously left, so why don't we just have it leave? And that arrow movement would give that carbocation plus Br minus. Okay, we formed one product right there. Can a leaving group just leave? Yes. Leaving groups just leave in an SN1, and in fact, this is the same exact step as an SN1 mechanism. From there, this molecule could react with here and give us an ether. In fact, let's show that. If these electrons reacted here, that would give boom, boom. Now, oxygen bonded here with a 2-butyl, but that would be a substitution product. where ultimately we just replace the bromine with this new group. New group there in place of bromine. That's obviously not what's going on here. By the way, this has problems because that's a strong base. That mechanism has flaws, but if that did attack there, it would be a substitution product. Instead, what happens here is this guy takes one of the beta hydrogens and acts as a base, not a nucleophile. And these electrons fall in here to make a second bond, a pi bond. And this electron movement would give, well, everything there now. We already formed the Br minus. Right here we're making the alcohol, the O takes the H, there's 2 lone pairs remaining. And right here the electrons are falling in to make pi bond, and there's your pi bond, and there's your alkene. So here we didn't just replace the bromine with anything. Instead, we simply removed it along with an H, and so we eliminated atoms from this molecule in an elimination reaction. We removed HBr. That's a formal assessment. We just did a dehydrobromination reaction. But again, we did not form HBr. Other things were formed. I just showed an E1. Okay, let's do a reaction coordinate diagram here. A, first intermediate would be B, only intermediate, and then final organic product would be C. A, B is a carbocation, higher energy. C, how does C compare to A? Well, C now has a weaker pi bond in place of 2 sigma bonds. We broke 2 sigma bonds in doing this reaction. Sigma bond to H and sigma bond to bromine. We could get out our calculator with some thermodynamic tables, but it looks to me like we're replacing 2 stronger bonds with a weaker bond. This molecule is less stable. It's going to be something like here compared to A. Okay, here we go. Boom. Leaving group leaves. Okay. Ionization. Leaving group leaves. And then the next step should be fast and easy. That should be your rate determining step. This should be fast. This reaction's got a positive delta H. This reaction is actually endothermic. Not favored by enthalpy. Okay, why is it called E1? Well, of the 2 substrates, how many are involved in the rate determining step? Well, the rate determining step only involves ionization of the alkyl halide, the leaving group leaving. Okay? The base is not involved in the rate determining step. Only 1 molecule is, and thus it's an elimination bimolecular. Elimination bimolecular, and then the base taking the H sometimes this elementary step is sometimes called the beta elimination because that's when the base actually takes the beta hydrogen, where the first step was leaving group leaving or ionization. Okay, What do you think of that mechanism? Do you think that's the mechanism for the model reaction? Well, no. Because primary carbocations are bad, right? We never want to form those unless for some reason we just have to. Very similar idea to our model SN1 reaction we showed. We're only going to want to form carbocations on secondary or better tertiary carbons. And of course, even better would be something that's resonance stabilized. Okay, another mechanism we could show is almost like an SN2. That is, this molecule is going to do something, but it's going to act as a base here, though. What if these electrons take the H, these electrons move in here, make pi bond, and kick that off all at the same time? What would all of that arrow movement give? Well, it would give all that. And that is where all steps are concerted. And no carbocation ever formed in this mechanism. And that is an E2. Because if we look at the reaction coordinate diagram, okay, you can label these. What do we have here? Reaction progress, some type of energy. This is A, call that B, A, B, B. And the mechanism here is just boom. What do we have? There's your activation energy. No intermediate. That's just a transition state energy. How many steps in this mechanism? Just one. This is the step. Both of these are thus involved in that one step. They better be. It's only one step. Since they're both involved, we call this a E2 elimination bimolecular. It's somewhat analogous to backside attack. Instead of this thing acting as a nucleophile and attacking the carbon and kicking off the leaving group all in the same, it takes instead the beta hydrogen, and those electrons in that bond fall in to make pi bond here, and that leads to expulsion of the leaving group. So we actually have 3 arrows here, all in a concerted one-step mechanism. No carbocation intermediate. And this is actually the mechanism for the model reaction, mainly because we would never want to do the other mechanism. We would never want to do a mechanism involving a primary carbocation. Okay. Is there another possible mechanism for this elimination reaction? Well, there is another one possible. It's not typically shown in a textbook, and it's actually wrong. But sometimes you guys will want to show this mechanism. So I'm going to go ahead and show it and say how it is wrong. All right. What if instead, though, the base took an H and the electrons stayed behind and we did a good old acid-base reaction and left an anion here plus the alcohol. That's just an acid-base reaction, right? Base takes the H, electrons stay behind on the atom as a lone pair. Did we do that previously? We did not. We never made an anion. The base never just took the beta H. No. So this is a third mechanism. From there, we could maybe say, then these electrons move in here and kick that off. That would give those two, right? But that is not the mechanism. That is neither E1 or E2. Now let's look at this leaving group. Okay, back over here. In which mechanism does the leaving group leave in the rate determining step? E1. What is the rate determining step? Leaving group leaves. E2. What is the rate determining step? Well, it's all concerted. Base takes H, electrons fall in, and leaving group leaves. Leaving group leaves in both rate determining steps. Over here. Here the rate determining step should be the first step, the difficult step, to make the charged intermediate. From there we're falling downhill. This should be fast. So in this mechanism, Lg leaves in fast step. And that's a big difference between the two mechanisms we'll be focusing on here in Organic 1, the two elimination mechanisms, E1 and E2. We will not be looking at this. It's more rare. This can occur if the beta hydrogen is acidic. Now over here, the beta hydrogen is not acidic. You would never look at this and say, wow, look at this acidic H. It's not. Then you might ask, well, why is the base taking the H then? Well, it's really not doing a traditional acid-base reaction here. And we would have to talk more about it. Here, this is a traditional acid-base mechanism, and the H has to be relatively acidic for that to take place. Much more difficult. It will only take place if the H is acidic. It could happen. We may see mechanisms like this in Organic 2. The key difference is understand that here the leaving group would be leaving in the fast step. Okay, we've already answered the first question. In which elimination mechanism does the leaving group leave in the rate determining step? Well, both E1 and E2. I should have let you answer that on your own because you really need to be looking back at the details there. Question 2, in which elimination mechanism is the beta hydrogen abstracted in the rate determining step? All right. I'll let you answer that there. Let's look at another example reaction. What if we take this alkyl bromide and it looks like we're heating it in this alcohol. Now that could be just solvent here. Alcohols can be solvents, heating it. Or we could heat it with no solvent at all. That is, just take this molecule and heat it. In either case, we can envision getting an alkene plus HBr. An elimination reaction. It's a dehydrohalogenation. We removed HBr. We actually also generated HBr. What would be the mechanism here? Well, if you remember for SN2, what did SN2 require? To react with the substrate with the leaving group, it required a strong nucleophile. Same thing for E2. E2 requires strong base. All right? It's actually a summary statement right here. Why does it require a strong base? Well, the base is involved in the rate determining step. The difficult step, and thus the base needs to be good, it needs to be strong to involved in the rate determining step. Well, this is not a strong base. Remember strong bases? Anions or sp3 nitrogens. Very analogous to what a strong nucleophile would be. No strong base. Thus, seeing that we did an elimination reaction and it cannot be E2, this mechanism must be E1. And here, with heat, what happens is the leaving group just leaves. Yes, it can just up and leave if it's a good leaving group, and depending on what we form. In this case, we will form a secondary carbocation. Not as good as a tertiary, but it can be formed. From there, we're just doing our E1 mechanism, which we did over here. Leaving group left. Except over here we had primary carbocation. What was next? Base took the H. Now the alcohol could act as a base, or we could use the leaving group. It could turn around and act as a base. Take the H, these electrons fall in, and we would get this product. Let me do something first, because over here I'm showing a trans product. Right here these groups look cis, but we have free rotation. How about if I rotate this first? Now often a rotation is not included in a mechanism, but to really understand why the product is trans, we see that. And we can go back to test 1. Right here the two groups are syn, and now they're anti. Anti would be preferred, right? So let that thing rotate first, then the bromide takes an H and these electrons move in. Put the double bond between, that will give the product. And then what else did we form right here? Well, we formed our HBr. And the alcohol did nothing in this reaction, and so it was just solvent. An inert solvent. And so this was an E1 mechanism, involved a carbocation. It's an elimination reaction. We could also call this a decomposition reaction. This molecule decomposed, it broke apart. That's a more general description. But when molecules start breaking apart, and when one molecule is converting to two, it's breaking apart, a general term for that is it's decomposing. Elimination in general would be the description of this. More specifically is elimination unimolecular, E1, because it was not an E2. Okay, again, summary statement. E2 requires a strong base. We'll say that many times going forward. Thermodynamics and entropy for elimination reactions. We already looked at thermodynamics. It's actually endothermic because the product is less stable than the starting material with this pi bond introduced and two sigma bonds being broken. What about entropy? So it's positive delta H. Entropy is positive delta S, right? We have gain disorder. Is that right? Right here, look at it. One molecule is going to two. Okay? So elimination reactions are actually disfavored. They're not favored by thermodynamics, but they are favored by entropy. And that's what sort of drives them, is the entropy. If we go back over here, if you include all reactants, you see that two reactants became three. And so you see we have an increase in randomness, we have a positive entropy. Now heat is going to favor this reaction because, what is it, delta G equals delta H minus T delta S. And you see that the delta S is magnified by temperature. And so if delta S is favored, heat it. Make it even more favored. Magnify that term by heating it. That's why molecules tend to decompose when heated, because if you heat this thing, just heat it up, it'll start breaking apart. This mechanism will take place, driven by heat. Not driven by thermodynamics. Okay. I'm going to stop this first video here because we'll be getting into the next topic, which we want to continue on the next couple of pages. And we will be looking at when regioisomers are possible from beta elimination reactions. In the intro reaction, regioisomer was not possible. There was only one beta hydrogen. Now these are identical, that's why I'm calling this only one. Only one type of beta hydrogen, only on one side. Okay? Actually, here there was 2, but we ignored it. Why did we ignore the H down here? Okay, why didn't we take this H and put the pi bond in down here? Well, that's because we haven't talked about that yet, and we need to talk about that. We see here, if we do a beta elimination of this leaving group, there's only 1 beta carbon, and the H's on that carbon are identical. And we can only put in the double bond between those 2 carbons. Of course, the carbon with the leaving group, but then the beta carbon where the beta H is, double bond there. In this case, we can put the double bond in on either side, alpha beta this way or alpha beta that way. Double bond here on the end, such as there, or the double bond between alpha and beta over here. So there's 2 types of beta hydrogens. If the double bond was put over here, it would give that product, but that product is stereogenic. And so it could either be E or Z, right? So while the first reaction only gives 1 theoretical product, and there's no stereochemistry here because it's not stereogenic, this reaction with beta elimination gives 3 possible theoretical products. These 2 being stereoisomers, and these 2 being regioisomers of that product. So which alkene will be formed in this second reaction here? That's what we need to look at. And we'll do that in the next video. We'll pick up here, Roman numeral 1, that point there, and then number 1, and then number 2. Okay, 2 very important ideas here to help us predict the regiochemistry and also stereochemistry of our products, of our alkene products. Okay, guys, please be looking ahead. So that's an introduction to E1 and E2 elimination reactions.